The very essence of periodic behavior is described as follows: a graph or a set of numbers that repeats in its trend and in its quantities. For example, if we take a look at this graph right here, we can see that the graph repeats itself after a certain set of time, or what we would call a period, hence its use in the term periodic. Alright? Now, we can derive that our period, or where it begins to repeat, is right about here, as this part repeats here. Since this graph repeats in its quantities and in its shape, we can assume that it will continue forever, and hence we refer to it as periodic. This graph here does demonstrate a similarity in trend in that it repeats in its length, so to speak. I mean, there's no scale here, but you get the idea. And it goes up each time. Now, it follows the same trend, however, it's not periodic, because this graph, or this section of the graph, is not repeated in its quantity. Down here, however, this is periodic. It has the same concept of going up, but then it goes back down and repeats exactly in its numerical values. This one is displayed again here, as is this one here, and the lines here. The graph itself repeats over and over indefinitely, which makes it periodic. We can derive here that the period is right here, because, it includes this guy, and that's where we started off. Periodic behavior is very prominent in the real world as well, as it happens all the time in nature and in just everyday things. Take, for example, the months of the year and temperatures that we see, right? In January, or your winter months, it tends to be cold. However, in spring, it starts to heat up. Then in summer, it's hot. And in fall, it is cool. This will, not factoring global warming or any of that, this will repeat indefinitely with the same structure. If we were to draw an approximate graph of the temperatures throughout the year, we'll have winter here, spring, summer, and then fall. Winter will be cold, spring will be warm, summer will be hot, fall will be cool. And then we'll continue again, winter, spring, summer, fall. This graph will repeat indefinitely as the seasons go on, and we'll have approximately the same data set, and this would be classified as a periodic trend or periodic behavior. One of the most common forms of a periodic trend that we use in math is the sine curve. And an example of a sine curve is what I've written down right here. We treat the sine curve as we would most other functions, and that we can write it out in function notation, and there are certain aspects of that notation that we can change in order to change the graph. There are a few big aspects of the sine graph that we like to use in the math community, the first of which being the sinusoidal axis. The sinusoidal axis is usually y equals 0. However, once you use translations, which we'll go into in a moment here, it can move up or down. Now, the next part is the amplitude of the graph. The amplitude describes how high or low the graph will deviate from the sinusoidal axis. The parent function always starts out with a point at the origin of your graph, and then it will go up, intersect the sinusoidal axis, down, and then revert to its original point on the sinusoidal axis. Here's some basic things that you should know about your basic sine curve. In your parent function, the period will always be 2 pi. One single completion, or one single period, of the function will always finish at 2 pi. The amplitude of the parent function is 1 unit. The graph will intersect the sinusoidal axis at x equals 0, pi, and 2 pi, and then every multiple thereof. Your minimum point, or your minimum value, will be at 3 pi over 2 and negative 1, and your max point will be at pi over 2 and 1. This here is a basic sketch of our parent function. It starts at the origin. Its maximum point will go up to y equals 1, since the amplitude is 1 unit. Your minimum point will be at 3 pi over 2 and negative 1, as the amplitude is also 1, so that'll go in either direction. Our intersection points are at x equals 0, pi, and 2 pi, and one complete period or instance of our function, starts at 0 and ends at 2 pi. In the general sine function, there are a few variables that we put in the standard form to help us more easily derive some of the basic aspects. Your period will always be derived from 2 pi over b, your b value being this one here in the standard form. Your a value is the amplitude. Your b value, again, determines the period by using 2 pi over b. Your c value is your horizontal translation of however many units to the right or left, and your d value, it determines your vertical translation, and that also affects directly the sinusoidal axis. Let's do a practice problem. Let's go ahead and graph the following function. Y equals 3 sine 1/2 of x minus pi plus 1. Let's jot down some of the basic information that we can gather from this. Our amplitude, or our a value, is 3. Our period is going to be 2 pi divided by 1/2, which is 4 pi. Our horizontal translation, or our c value, is pi. And then our vertical translation is 1 unit up. Now that we have our basic information, let's go ahead and graph it. Let's begin by labeling our x-axis. Our period is 4 pi. Half of 4 pi is 2 pi. Label pi, and 3 pi. Now that we have our x-axis, let's begin labeling our y-axis. Our sinusoidal axis will be at the y value of the vertical translation, which is 1 unit up, so our sinusoidal axis will be at y equals 1. Let's draw a dotted line there. Our amplitude is 3 units in both directions, so let's draw 2 lines 3 units away from 1, one of which being 4, this graph is not to scale, and then the other being -2. Let's draw our somewhat parent function using these parameters, then we'll do our horizontal translation. Again, this graph is not to scale. So now that we have our basic parent function here, we're going to move to the right pi units. So let's take each of these points. For simplicity's sake, we'll just use our beginning point and each of our intersections and our maximum minimum values. Let's go ahead and use this center point here, and we'll translate it pi units to the right. This one, pi units to the right. This one, pi units to the right. And this one, pi units to the right. Now let's fill in. Now we are left with some space here, so let's fill it in as it goes along with the trend. Prior to going up, it comes up to the point on the sinusoidal axis. So let's continue our trend, and there you have it. Here is our function, y equals 3 sine 1/2 of x minus pi plus 1. In this practice problem, it asks us to derive a sine graph by using real-world information. All we have to do is work backwards with what we're given. Let's begin by jotting down a few of our given things. The radius of our Ferris wheel is 10 meters, and that's going to be the amplitude of how high or low the light can possibly achieve. So our amplitude, or our a value, is going to be 10. Now that we have that, let's derive our sinusoidal axis, or our center of the graph. That is 12 meters above the ground. That is going to be the center point of rotation around which our light is going to go. So that would mean that our d value, or our vertical shift, is going to be 12 units up. So positive 12. Since we are to assume that our light begins at the very bottom point, we're going to have to translate our graph to one side. Since our basic graph looks like this, and we're going to start at our lowest point, let's continue the graph this way a little bit. not scale. And this is our opening point. We're going to have to translate it so that this is our opening point. Now, we'll get around to that in a little bit here once we have our x values figured out. So stay tuned for C. Our b value is going to have to be derived in reverse. For 2 pi divided by some value is going to equal 100 seconds. So let's solve for that now. To solve for Mr. Question Mark here, it's going to be 2 pi over 100. So our b value is going to be 2 pi over 100. Now that we have these parts laid out, so our equation is going to be our a value, 10, times 2 pi over 100. Our b value can be simplified to pi over 50. So 10 times pi over 50 x minus, we're yet to derive our c, so let's just leave that blank for now, plus our d value, 12. Now that we have that set out, let's go ahead and graph it so that we can visualize what our c value is going to be. Let's go ahead and label our x-axis here. Our period is 100 seconds, half of that being 50, 75, 25. We're going to go up, meet, down, finish. Ignore that there. So here is our current function. Now let's go ahead and translate it over so that our opening point is going to be our lowest point. Let's draw it. Low point, meet, maximum, meet, low point. So this is where we're at now. What happened here is that each of these points translated 25 units to the right. So that means our c value is 25. So to summarize what we just did here, we derived each of our key aspects of our equation from what we were given, jotted them down as their values, then we went through, derived our b value completely, graphed it, derived our horizontal translation, and put it all together into our mathematical function here. Now that we have it labeled as a true equation, our job is finished.